1.5. Today's topics will be pattern recognition, function building, and evaluating functions. When given the first pattern, there are two questions you would need to ask. First question, how many blocks are being added to each figure? We'll see that figure 1 has 5 blocks, figure 2 has 6 blocks, and figure 3 has 7 blocks. Therefore, we can conclude that 1 block is being added to each figure. How many blocks did I start with? Well, the common misconception here is to look at figure 1 and say you started with 5 blocks. However, the 5 blocks occurs after the first figure. Therefore, we have to go back to step 0. We'll have to subtract 1 block. We can conclude that we begin with 4 blocks. Remember, the starting value will always be at figure or step 0. Now let's fill in the table. At figure 0, we know that we have 4 blocks, so we'll write a 4 there. At figure 1, we have our 4 blocks, plus we added 1. At figure 2, we had our 4 blocks, and we'll add 1 twice. Now at figure 3, we'll start to abbreviate this process. So instead of writing 4 plus 1 plus 1 plus 1, we're going to write 4 plus 1 times 3, because repeated addition is the same as multiplication. If we continue this on down, and please notice that we jump from 5 to 10 to 25, we'll see that in the 10th figure we have 4 plus 1 times 10, and the 25th is 4 plus 1 times 25. The point of building the process in the table is to determine the function rule for the nth term. This is the very bottom process that we'll have. If we look at the pattern, we'll notice that we have 4 plus 1 times n, and we'll write that just 4 plus n. Now we'll complete the total blocks to the right. And next we'll use the table to answer a few questions. Is the data discrete or continuous, and why? We know that the data is discrete because the independent variable or figure number are the counting numbers, 0, 1, 2, 3, etc. It wouldn't make sense for 1.5 or 1.7 figure numbers in this situation. What is the reasonable domain and range? Because the data is discrete, we'll simply just write a list. The domain or x values are 0, 1, 2, all the way up to infinity. The range or the y values are 4, 5, 6, all the way up to infinity. Now let's use the function rule to determine the number of blocks in the 225th figure. So what we can do, and this is a relatively easy problem, but it's going to get more difficult, but we'll still use the same procedure. Let's use the function rule, total blocks equals 4 plus n. Then what we're going to do, because n represents figure number, we're going to input 225 into n. We'll plug that in, evaluate 4 plus 225 is 229, and we can write this as an ordered pair, 225, comma, 229. Now let's explain how to determine which figure, if any, contains 1,496 blocks. I've written 3 options here. The first option, since we started with 4 blocks, we subtract 4 from 1,496, giving 1,492. Because 1 block is added each term, there are 1,492 terms. So it would be the 1,492nd figure. The second way we could do this is notice that the input, the figure number, is always 4 less than the output. Therefore, 1,496 minus 4 is 1,492. And lastly, and this is what we'll start doing throughout the year, we're just going to solve the equation. We're going to write the equation and solve 1,496 equals 4 plus n. Now let's look at pattern building number 2. This time we're going to observe what happens when dimensions are changed of a rectangle. There are three possible variables here, but we'll only use two. The three possible values that are changing are figure number, area, and height. We'll use area with respect to figure number. So we're going to use the height, but not as one of our variables. What term is remaining constant? We'll see that the base is always 3. You may see patterns later on where two dimensions are changing, and we can deal with that as well. Now let's build the table for our pattern number 2. In figure 1, the dimensions of the rectangle are 3 by 2. In figure 2, the dimensions are 3 by 4. In figure 3, the dimensions are 3 by 6. Well, it's pretty easy to see what the pattern is, but what we need to do for patterns much farther along that we can't actually draw, what we need to do is notice how the variable in the height relates to the figure number. So let's look at the height and let's see how that relates to the figure number. We'll notice that the height is always twice the figure number. Therefore, in the process, we'll just double the figure number. So for figure 4, we can just double the 4, which we get to 8, so it's 3 times 8. In figure 5, we'll double the 5 and get to 10, so 3 times 10. For figure 10, that would be 3 times 20. For figure 25, that'd be 3 times 50. So the total areas are 24, 30, 60, and 150. So the process for the function rule for the nth figure is 3 times 2n, which is the same as saying 6n. Once again, we'll ask if the data is discrete or continuous. This is also discrete because we're only going to have the counting numbers. The numbers between 0, 1, 2, 3, etc., those are not going to make sense for this situation. And what is the reasonable domain and range? It's very similar to before. It's just a list. 0, 1, 2, 3, all the way up to infinity for the domain. And the range will start at 0 and 6, 12, 18, all the way up to infinity. Now let's use the function rule to determine the total area in the 225th figure. We'll basically do the same thing as we did before. We're going to take our total area equals 6n. We're going to input 225 in place of n. And we're going to evaluate that. So the total area is going to be 1,350 square units. So we could write the coordinate 225, comma, 1,350. Now we're going to explain how to determine which figure, if any, has an area of 625 square units. Well, the figure begins with 0 blocks. If we went back to step 0, we would see that this is just 3 times 0. So we don't have to add or subtract anything. We'll simply determine how many times 6 will divide into 625. Well, we know that 600 will be divided by 6, which is 100. The remaining value there is 25, but 6 will not go into 25. So there is not a term number which has an area of 625 square units.